So we start lecture 11 and lecture 12. And here we deal with circular motion. Now you can look at the videos on this link here. It shows you circular motion for different objects. Okay, and once you have looked at the videos, you can try to answer these three questions here. Okay, so we have videos of moving objects, and the objects are moving in a circular path. So for each case, you're trying to identify the force that kept the object moving in a circle. And for the three videos in the link, there will be three different forces. Okay, and then for question 2, it's asking you to sketch the direction of the particular force at different points on the circular trajectory. Okay, so the emphasis on the word direction. So the object is rotating in a circle, so it makes a circular path, and it has some force acting on it, and the force is acting in different directions at different points on the circle. Okay, so you can try to draw arrows to represent the force at these different points. Okay, and that's important, as we'll see later. And then question 3 asks you whether the object is accelerating or not. Okay, and here the answer is yes, the object is accelerating in all three cases because the object is changing direction. So if the object is changing direction, it automatically means that the velocity is changing. Okay, it may be moving at the same speed, but it's changing direction, so velocity is changing, and that implies that the object must be accelerating. Alright, so let's look at this diagram now. So suppose we have an object moving in a circle, and these 2 points are for the object during its motion. Okay, so these two, the diagram shows 2 successive positions of a particle. Alright, and we have these 2 arrows showing you the velocities of the particle at these 2 points. So based on the information, we are trying to figure out the direction of the acceleration, and we are given 4 choices. So how do we solve this problem? Here, let's continue. So suppose this is the circular path that the object is traveling upon, and these are the 2 points from the previous slide on the circle. Okay, so let's see the 2 dots, they lie on the circle, and we have the arrows showing the direction of the velocity at these 2 points. And a reminder that acceleration is change in velocity over time. So here we are dealing with 2 vector quantities. Both the velocities are vectors. So when you do acceleration equals delta v over delta t, you have to do delta v as a vector quantity, but is subtracting 2 vectors. So delta v is v final minus v initial with vector signs. And then delta t is the time. So that's the time it takes to go from the first dot to the second dot. Now, let's look at the delta v at the top, v final minus v initial, and we have to perform vector subtraction. Alright, and reminder that vector subtraction is really the same as adding a negative vector. So we are trying to do v final minus v initial. That's the same as doing v final plus negative v initial. Now, so let's start by drawing v final. So you can look at the arrow for v final here. So you are just drawing it again on this side with the blue arrow showing the same direction. And then you draw v initial from the end of v final. So we are using the head to tail method. So v initial is pointing up, sort of vertically up, slightly slanted. But then what we are interested in is not v initial, we are interested in negative v initial. So we draw negative v initial with this purple arrow, and it's pointing exactly opposite to v initial. Okay, so you can compare the v initial on the left with the negative v initial on the right, and they're the reverse of each other. So we have plotted v final and negative v initial, and now we connect them with the one big vector, and that's the acceleration vector. Okay, so that's the direction of the acceleration that points from the starting point of v final to the ending point of negative v initial. Okay, so this is the acceleration vector. That's the same as v final minus v initial. Okay. All right, so in the picture here, we can draw the acceleration vector. That's the red arrow pointing this way here. Okay, so here we have the same triangle as from the previous slide. We have the velocity triangle and the acceleration arrow. Now, this is the enlarged picture. We have the 2 points on the circle and we have the acceleration pointing kind of like this. So let's extend this arrow. Okay, so if we extend the acceleration arrow, we'll see that it passes through the center. Okay, so we have a circular path and the center of the circle is the point that the acceleration vector passes through when you extend it. So going back to the original question, so we were given the 2 velocity vectors and we were given 4 choices for acceleration. The answer is D. That's the direction of the arrow that shows the acceleration. Okay. Okay, so here's a summary. So let's start with the picture on the left. We have this black dot that's traveling in a circular path, okay, shown in the picture as counterclockwise rotation. And this is the direction of the velocity at each point. So the green arrow represents velocity. And you can see the velocity always makes a tangent to the circle. Okay, you can check all 3 points shown and the velocity is always tangential to the circle. And then we have the net force, and you can see the net force always points to the center. Okay, and you can see the note here about the net force. The net force is required to keep the object moving in a circle, and the net force is directed towards the center of the circle at all points. So it doesn't matter where the object is in the circle, the net force changes direction and it points to the center of the circle. Okay, and this other note at the bottom tells us that suppose you remove the net force at this point at the bottom, then the object doesn't move in a circle. It just keeps moving in a straight line. So in other words, the net force is responsible for changing the direction of the particle and making it move in a circle. Okay, so without the net force, it just keeps moving in a straight line. And if you have a net force that points to a center, the path curves. And if you have the right amount of net force pointing to the center, it curves sufficiently and makes a circular path as shown. And in this picture on the right, it shows you something similar, except that instead of the net force, it shows you acceleration, which isn't surprising because we know from Newton's second law that net force and acceleration must point in the same direction. Okay, so here you can see that at all points on the circle, the acceleration points towards the center, just like the net force does. And then we also have the arrow for the velocity, that's tangential. Okay, all right, and another important point about the direction of the velocity and the acceleration. So the acceleration is effectively the radius of the circle. It points to a center and then connects to the edge, and the velocity is like a tangent. And from geometry, you know that the tangent and the radius makes a 90-degree between them. So this tells us that if you find the angle between the acceleration and velocity at any point in the circle, you end up with 90 degrees, a right angle. All right, and another important point that what we have studied here is for an object moving in a circular path at a constant speed, which is known as uniform circular motion. Okay, so that means moving at a constant speed. So the velocity is changing because the direction of the particle is changing, but the speed is the same. It's moving at the same speed all throughout the circle. And if it is not moving at the same speed, you would call it non-uniform circular motion. Okay. But now let's look at circular motion at constant speed. So let's look at uniform circular motion first. Okay, now back to the acceleration here. So the acceleration points to a center for an object in uniform circular motion. And suppose the radius of this circle is r, okay? And the acceleration makes the velocity change direction, okay? So this is what we know about the acceleration. The direction of the acceleration always points to a center, so we have covered that already. And the magnitude of the acceleration is given by this quantity, the v square over r, where v is the speed of the object, r is the radius. Okay, so we won't derive the magnitude in this lecture, but if you derive the acceleration in terms of the speed and the radius, you will see that the magnitude turns out to be v square over r. Okay, so this also means that if you have an object moving at a bigger speed and at a certain radius, you would need to create a bigger acceleration to maintain that circle. So if the acceleration is not big enough and the particle won't move in a circle of this particular radius, it would have to move in a circle of a different radius. Okay, All right, so velocity and radius both together determine how much acceleration you need, which in turn tells you how much net force you need to keep the object moving in a circle. All right, and this acceleration here points to a center. So the name we assign to it is called centripetal acceleration. All right, centripetal means pointing to the center. Okay, so the acceleration is always pointing to the center for circular motion. So it's known as centripetal acceleration. Okay, and correspondingly, the net force is known as centripetal force. Okay. All right, so in circular motion, the net force has to point to a center, and that force is called centripetal force. So when you see the term centripetal force, you know that it's we are referring to the net force that's pointing to the center. So let's try this question. We have a ball on the end of a string, and the string is swung in a vertical circle. All right, so you make a vertical circle by swinging the string. Okay, and we know the ball is accelerating because of these three options. So option A, the speed is changing. Option B, the direction is changing. Option C, the speed and direction are changing. Okay, so which is the right answer? So the right answer is the direction's changing. Okay, so if the direction changes, the velocity must be changing, which means the ball is accelerating. However, let's think of option A and option C. Okay, so option C said both the speed and direction are changing, and that's also possible. It all depends on how fast you're swinging the ball. Okay, so you could be swinging the ball in a way that it maintains a constant speed, and then the speed would be not changing and the direction would be changing, which would make answer B the right answer. However, you can also swing the ball in a way that both the speed is changing and the direction is changing. So it could be moving faster at the bottom of the circle and slower at the top. You could do that too. In that case, C would be the right answer. The speed and direction are both changing. However, the question doesn't tell us anything about the speed. It could be the same, it could be different as it moves. So B is the safe answer. The direction is definitely changing. The speed may or may not be changing. Okay, next part of the question. So we have the same ball again in a vertical circle. We are trying to figure out the direction of the acceleration of the ball. So option A, the acceleration makes a tangent to the circle in direction of the ball's motion, and option B points towards the circle. And as we have seen earlier, the acceleration in circular motion must point to the center of the circle. That gives us option B as the right answer. Next problem, we look at a coin sitting on a rotating turntable. So this large disc is a turntable. It's turning counterclockwise, shown by this arrow up here. And we have a coin that's sitting somewhere close to the edge of the turntable and also rotating with the turntable. Okay, so the question's asking which arrow among A, B, C, D gives the direction of the frictional force acting on the coin. All right, so let's try to understand where frictional force comes in consideration. So this coin is moving in a circle. So you can, if you trace the path, you will see that this coin traces a path counterclockwise, goes around the circular path. So if the coin is moving in a circular path, it must have a centripetal force. Okay. All right. So where does the centripetal force come from? What provides the centripetal force? Okay. So if you think about it, the force that connects the coin to the turntable is friction. So the friction makes the coin turn with the turntable. So basically, friction is responsible for changing the direction of the coin as it moves. Okay, so without friction, the coin would be moving in a straight line and then roll off the table. So here, effectively what we are saying that friction provides centripetal force. Friction acts as the centripetal force. So looking at the picture, we can see the centripetal force must point to the center. That's the direction shown by option D, which also means friction must point to the center as well. So we have this. The friction acting on the coin points to the left towards the center, option D. Then we have more examples. So we have in example 1, a car traveling on a horizontal surface, and it's curving, okay, on a country road. Okay, so we have two pictures of the car. On the left we have a picture of the car, and there's a frictional force pointing to the left. So here let's draw a circular path for the car. So this dotted line shows you the path of the car. Okay, and let's just assume it's traveling in a perfect circle. Okay, it's not necessary to travel in a perfect circle, but let's assume for simplicity. Okay, so this red dotted line, let's assume is the path that the car travels in a circle, and the friction acting on the wheels of the car must point to the center. So again, like in the previous example with the coin and the turntable, the friction acts as a centripetal force, and that points to the center of the circle. And here the free body diagram, that's the black dot here with the arrows, gives us a better illustration of the forces. So we have three forces acting on the car. We have the weight and normal force pointing up and down, and then we have a horizontal force, the friction, pointing to the center. Okay. All right, so this is what the free body diagram looks like for the car moving in a circular path. And now, example 2, we have Ferris wheel. So we have a car at the top of the Ferris wheel, and it's also moving in a circle. Okay, so we're talking about this car here at the top of the ride. Okay, put a red dot here. All right, and then if you draw the free body diagram for this car at the top, so basically if we draw a free body diagram for the red dot, this is what it will look like. So there are two forces acting on this object, on the red dot. There's the weight, as usual, that's pulled by gravity, and there's a normal force that points up. Okay, so a person sitting in the top car has a normal force from the surface of the car pushing him up, and the weight of the gravity pulling him down. Okay, so these are the two forces. However, you can see in the picture, we have drawn the two forces not of the same size. Okay, so obviously the weight is bigger than the normal force. Okay, now we have already seen that weight and normal force can have different magnitudes. They can be the same or different depending on the scenario. Okay, so in this scenario, how do we know that the weight is bigger than normal force? How do we know they are not equal, or how do we know that normal force is not bigger? It all depends on the acceleration of the person. So remember, when we studied Newton's laws and normal force and weight, we determined that if the acceleration of the person is pointing up, the normal force is bigger than the weight. And if the acceleration of the person is pointing down, the weight is bigger than the normal force. And if the acceleration of the person is 0, weight and normal force are equal. So going back to our setup here, we have this Ferris wheel and it's rotating in a circle, and when at the top of the wheel, this person has a centripetal force pointing down. Okay, so in other words, the acceleration of the person at the top of the wheel is pointing towards the center. It's the centripetal acceleration. So this object is accelerating downwards when he's at the top of the circle, which automatically means the weight should be bigger than the normal force. And that's the reason that we have these two arrows of different sizes, because we know that weight has to be bigger, otherwise the acceleration can't point to the center. And to add to this question, if we have a person at the bottom of the wheel, so down here with the blue arrow, and the Ferris wheel is rotating as before, in that case, the acceleration of the person will be pointing to the center of the wheel, which is pointing up. Okay, all right, so in that case, at the bottom of the wheel, the normal force will be bigger than the weight because the acceleration is pointing upwards. All right, and then at these other points in the circle, the acceleration will be pointing diagonally, which will make the normal force somewhat bigger or somewhat smaller depending on where you are on the wheel. Okay, so let's look at the problem with the car and try to solve this problem. So here the car is traveling on a curve, and the curve has a radius of 150 meters. Okay, so I'll just draw the circle that I had in the previous slide. So this is the circle, a track of radius 150 meters, and the car is traveling along this path at some constant speed. Okay, all right, and it says the coefficient of static friction between the tires and the road is 0.4. All right, so based on this information, we are trying to figure out the maximum speed of the car at which it can travel in this circle. Okay, so if you think about this, as the car travels faster and faster, the frictional force has to get bigger and bigger to keep the car confined in the circle. So if the car is traveling too fast, then the frictional force cannot get big enough, and the car won't be able to maintain this circular path. It will end up curving over a bigger circular path. Okay, so that's something to keep in mind when you're making a curve while driving. For example, traveling from a highway to an exit, which are usually curved. They usually post speed limits, and these are some of the quantities, some of the factors that determine the speed limit. Okay, so the curve of the path, which is effectively the radius of the path, and also the coefficient of friction. Okay, so back to the problem here. We want to figure out the maximum speed possible for the car to make this to stay on this curved path. So let's start by doing this. We have the free body diagram shown up here, and let's look at the y direction. So once we have the free body diagram, then we add the vectors in the y direction to find net force in the y direction, and then we'll do the x direction separately. So in the y direction, this is what we have. There are two forces, normal force minus mg. And we also know the net force in the y direction must be 0. And how do we know this? We know this because the acceleration in the y direction is 0. Okay, so there is acceleration in the x direction, but there is no acceleration in the y direction. And I know this because the car is staying on the surface itself. It's not going up or down. So there is no motion in the y direction, which tells us there is no acceleration in the y direction, which tells us that the net force in the y direction must be 0. Okay, so we have 0 equals normal force minus mg. That tells us normal force must equal mg. So for this scenario, normal force and weight are the same. Okay, all right, then let's do the x direction. Now in the x direction, there is just one force, the friction here. Okay, so we said net force in the x direction equals friction, but then there's more. This frictional force is the same as the centripetal force, because you can see in this other picture, this frictional force points to the center, and it's the only force that points to the center, and it's responsible for keeping the car moving in a circle. So this friction is the centripetal force. Okay, so we are going to replace the net force with centripetal force, because remember, centripetal force really is a net force that points to a center. Okay, so we have the equation for centripetal force is mass times centripetal acceleration. Okay, that's equal to friction. And then we also know that the centripetal acceleration, let's call it AC, is the same as v square over r. Okay, and for friction, we know the maximum possible friction is the coefficient multiplied by the normal force. Okay. All right, so remember that static friction you can calculate the maximum possible static friction using the coefficient multiplied by normal force. So friction can be less than this number, but it can be more than this number. So this is the upper bound for frictional force. So for this problem, we are trying to find the maximum speed. So let's plug in the maximum friction into the equation. Okay, so this is what we have. We have mv square over r equals mu times n. Mu is 0.4 here. So let's mark this in the question. Okay, and then again, you can see that we have a normal force in this equation here, and we already know normal force is the same as mg. So replace the n, the normal force, with mg. Okay, so now we have an equation with mv square over r on the left side, mu s times mg on the right side. And we can cancel out the m's on both sides here. Okay. And then we are solving for v, the maximum speed. So move the r to the other side, take the square root, and we get this. The maximum speed equals square root of mu s times g times r. So now we know all the required quantities. Mu s is 0.4, g is 9.8, and r is 150 meters. So you can plug all this in. That will give you the maximum speed permitted for this car to make a circular path. If it's traveling at a bigger speed, it won't be able to maintain this circular path. It will end up with a path of a bigger radius because the friction isn't strong enough to make the vehicle carve sufficiently. Okay, now this is the setup we have. We have a car of mass 1500 kilogram. It goes over a hill with the speed of 20 meters per second. So that's the V, okay, and the direction shown. And let's assume that the hill is approximately circular and the radius of the hill is 60 meters. So we have basically a car with a given speed located at the top of a circle, okay, and the radius of the circle is given. Okay. All right. So we are trying to calculate the normal force of the road on the car. Okay, now let's before we continue, let's look at the acceleration of the car. So the car is moving in a circle, which means there has to be a centripetal acceleration. So the centripetal acceleration must point to the center. So when the car is at the top of the hill, the acceleration must be pointing down. Okay, so if the acceleration is pointing down, this tells us that the normal force must be less than the weight. All right. So let's calculate and try to figure out exactly how much the normal force is. Okay, so this is what the free body diagram looks like. There are just two forces, normal force and weight, acting vertically, and the weight is 14,700 newtons. You can find it by calculating the product of the mass with g. Okay, and the normal force has to be less than that. So we draw a smaller arrow for the normal force. And now let's write down the vector sum of the forces. So let's write down the net force as normal force minus weight. Okay, so we have net force equals normal force minus mg, and then for net force we plug in negative mass times acceleration. Why do we put a negative sign? Because we can see the acceleration is pointing down. So the acceleration must have a negative value. So we put a negative times m times acceleration. And we put a c for the acceleration because this is centripetal acceleration. All right, then the next line, you replace the ac, the acceleration, with v square over r. Okay, so that's the equation for centripetal acceleration. That's centripetal acceleration is v square over r. And now you solve for the normal force. So rearrange the equation and you get normal force equals mg minus mv square over r. And let's plug in the numbers now. So the mass is 1500 kilograms. The v is 20 meters per second. The r is 60 meters. So plug on these numbers, calculate, and you get this. So when you do the calculation here, then value that you get is going to be the normal force. It turns out to be 4,700 newtons. And you can see it's a lot less than the actual weight, which is what we expected. The acceleration is pointing down, which means the weight should be bigger than the normal force. and normal force is 4,700 compared to weight of 14,700. Then similar problem, except that this time the car is at the bottom of the hill and the radius of the hill is still the same and the speed is still the same. So this time the difference is that since the car is at the bottom of the hill, the centripetal acceleration must point to the center, and the center is pointed above the hill, above the car. So the acceleration is pointing up. And if the acceleration points up, this tells us normal force should be bigger than the weight. So let's start like before. So we have the weight of 14,700 newtons, and the normal force should be bigger than that. So here we haven't drawn a big arrow, but you can pretend that normal force is bigger. We'll calculate it. And you proceed with the same strategy. You write down net force equals normal force minus weight, and then replace the net force with mass times acceleration. And this time you plug in a positive acceleration because the acceleration is pointing up. Okay? And then replace the acceleration with v squared over r because it is the centripetal acceleration. And then rearrange, and you get normal force equals mg plus mv squared over r. Then plug in the numbers for mass, g, then v and r. We get 24,700 newtons. Next we look at Newton's law of gravitation. So Newton's law of gravitation says if you have two objects of mass m1 and m2 and the centers of the objects are separated by a distance of r, then the forces will attract each other with forces of gravity. Okay, so you can see the two arrows in the picture. You can the two masses apply forces on each other. Okay, so the arrow on m1 is the force exerted by object 2. Okay, so we call it force of 2 on 1. And the arrow on m2 is the force exerted by object 1 on object 2. Okay, so effectively the two arrows form an action-reaction pair as seen by Newton's third law. So Newton's law of gravitation says just because these two objects have masses, they will attract each other with a gravitational force. Okay, and this force is always attractive. So we can look at the text in the box here. So if two objects with masses m1 and m2 are a distance of r apart, the objects exert attractive forces on each other of magnitude this quantity. So the magnitude of the force is given by uppercase G, which is a constant we'll see later, multiplied by the two masses divided by r square. So this gives us the magnitude of the forces. Okay, and the directions are always pointed towards the other mass. Now the constant G here, uppercase G, so this is called the gravitational constant, and the numeric value of G is this 6.67 times 10 to the negative 11 Newton meter square over kilogram square. So this law of gravity applies to any two objects that have masses. It can be two pens maybe, or it can be the wall and a tennis ball. Any two objects that have masses, they will have a force of gravity between them. So that means they will attract each other. However, when you're calculating this force, you have to factor in the quantity g. And you can see g is a really small number. It goes into the order of 10 to the negative 11. So this tells us that if for regular masses, like masses of kilograms, and you plug in the correct value of g, you will get a really small force. So that's why when you have two objects together, like two bottles next to each other, so sure, there is a force of attraction between them, but this force of attraction is tiny. So the other forces acting on these objects, like air or friction or other similar forces, will be a lot stronger than the gravitational force. So the effect of this gravitational force is usually not visible for such cases. However, if you have two masses or one mass that's really big, like think of the mass of the Earth, that's in the order of 10 to the 24 kilograms, so that's huge. So if you plug in the mass of the Earth in this equation, then even with the small value of g, you still get a substantial force. And that's what we see when we drop an object. It falls towards the Earth because the Earth is applying a gravitational force. So sure, all two objects apply gravitational forces on each other, but unless the mass is really big, this gravitational force is not going to be substantial. So you won't be able to observe it. And that's why we observe the gravitational force from the Earth just because of its mass and not from two tiny objects. Okay, so let's look at this setup now. So here we have the sun and we have the Earth, and the distance between the sun and the Earth is this much, 149 million kilometers. And we know the Earth orbits around the sun. Okay, so the Earth is traveling approximately in a circular path. So there has to be a centripetal force that pulls the Earth towards the sun, the center of the circle. Okay, so now if you look at the sun and the Earth, they're not in contact with each other, and there is only empty space between them mostly. So the only force that acts on the Earth is the gravitational force from the sun. Okay, so the Earth and the sun are pulling each other with gravitational forces. Okay, so we draw an arrow for the Earth showing a force of gravity pointing to the center of the sun. Okay, and this force of gravity must also act as the centripetal force. So using this information, we're going to calculate the mass of the sun. All right, so we have the free body diagram of the Earth. It's just one force that points to the center of the sun. So we write it like this. The net force acting on the Earth is the force exerted by the sun on the Earth, which is the gravitational force, Fg. And then for the gravitational force, we can replace it with the equation from the previous slide. That gravitational force equals uppercase G multiplied by the two masses of the sun and the Earth divided by r square, where r is this distance given between the sun and the Earth. And we are not done yet. For the net force, we can replace it by mass of the Earth times acceleration. Here we are using only the mass of the Earth because we are calculating the acceleration of the Earth. Okay, we are calculating the speed of the Earth. We are looking at the forces acting on the Earth. And the acceleration is centripetal acceleration because it points to the center. We can replace it with v square over r. So now in this equation, you can see that on both sides of the equation we have the mass of the Earth. So let's cancel it out. Okay. And then rearrange the equation, solve for the mass of the sun, and we get this. Mass of the sun equals v square r over g. Now we know what r is, and g is a constant. We can look up the value. But what's v? What's the speed of the Earth? So let's figure that out as well. All right, to understand the speed of the Earth, let's look at the next concept. We are going back to circular orbits. Let's look at the concept of period and frequency. Okay, so let's start with the first term, the time period, also called just the period. It is the time taken by an object that's making circular motion to go around in one complete revolution. Okay, so basically you take an object, it completes one full cycle. The time it takes to do so is called a time period. A symbol that we use is uppercase T with units of second. And frequency is a term related to the period. Frequency is just 1 over the period. So it's called the reciprocal period. And the unit of period is seconds. The unit of frequency is 1 over seconds, also called the hertz. So we'll see frequency later. We'll just introduce it for now. So the period tells you how long it takes to make a full cycle. So a longer period means that it takes a longer time to complete a circle. But frequency is the opposite. A longer frequency, a bigger frequency means it takes a shorter time to complete a circle. Okay? In other words, the frequency tells you how many cycles the object completes in 1 second. Okay, so if you have a larger frequency, that means the object completes more cycles in 1 second. And a smaller frequency means the object completes fewer cycles in 1 second. Okay, so frequency and period, they're just reciprocal of each other. Now let's look at the picture down here. So we have an object moving in a circular path of radius r at some constant speed of v. So to find the speed v, we can use the usual formula. Speed equals distance over time. And this applies because there is no change in the speed. The speed is constant. So when we have a constant speed, we can just do speed equals distance over time. Now, let's look at some object here that starts from, let's say, this point and then goes around, completes a circle, ends up back at this point. Okay, so this object here completes a full cycle. So if it completes a full cycle, the distance it travels is the same as the circumference of the cycle, of the circle. So for the distance, we plug in the circumference. And how much time does it take to complete the circle? It takes a time of the period t. So for the circumference, from geometry, we know that circumference equals 2 times pi times r. So let's plug that in. And you divide by the period t, and you get this formula here. So the speed of circular motion is this, 2 pi r over t. Okay. And this is what we'll use to find the speed. All right, so back to our problem. So this is the equation we established for finding the mass of the sun, where it has the term v, which is the speed of the earth. Okay, and we established that the speed of the earth is given by 2 pi r over t, because it's moving in a circular path. All right, so we replace the v square with 2 pi r over t square in the equation. Then let's plug in our numbers. So r is given is 149 million kilometers. So when you convert to meters, it becomes 149 billion meters. And g is the constant, the gravitational constant that we defined earlier. All right, so we still have one quantity that we need to list down, the t, the period. Okay, so how long does the earth take to make one full cycle around the sun? Okay, and that's going to be 1 year, right? But we have to convert 1 year to seconds, okay, because the units that we're using are seconds and kilograms and meters. Okay, so we have to convert 1 year to seconds. So you do the calculation. So 1 year is 365 days, and each day consists of 24 hours, and each hour consists of 60 minutes, which consists of 60 seconds. So you multiply 365 with 24, with 60, and with 60 again. That will give you this number, 3.15 times 10 to the 7 seconds. That's the period of the earth. So that's the value of t we plug in here. Okay, so let's complete the calculation. So this is the equation we derived for the mass of the sun, and these are the values that we have obtained so far. So plug them all in and do the calculation. Okay, and we get this 1.97 times 10 to the 30 kilograms. Okay, so just for reference, this is about 1,000,000 times bigger than the mass of the earth. Okay, so this is an enormous mass, huge. It's the order of 10 to the 30 kilogram, while the mass of the earth is 10 to the 24 kilograms. Now let's also look at the connection between weight and the gravitational force that we have studied. Okay, so let's look at this setup. Suppose this is the earth, the blue circle, the radius and the mass are given. Okay, and we place a small object on the earth. This could be like a book, for example, on the surface of the earth of mass m0. Okay, so this m0 mass is being pulled down by the gravitational force from the earth. Okay, if we draw an arrow pointing down to the center of the earth. So this is the gravitational force from the earth, so we call it Fg, but it is also known as the weight of the object, because like we said earlier, weight is the same as the force of gravity. Okay, so we write W, the weight, as Fg. Okay, so W equals Fg, and then we know that weight is mass times g. So we have seen that earlier. And then for gravitational force, we plug in the expression that we derived a few slides ago. G times mass of the earth times the mass of the other object divided by r square. And here r is the same as the radius of the earth, because we're assuming that the m0 lies on the surface of the earth. Okay, if m0 was located further above, we would plug in a bigger number in place of the radius of the earth. Okay, so continuing, we see that the m0's cancel out on both sides. Okay, and we have an equation for just lowercase g. Okay, so this equation tells us how to find the acceleration of free fall using the mass of the Earth and the radius of the Earth. Okay, so far we have used the value of g, 9.8 meters per second, in our calculations, and we just assume that it's a value that's constant near the surface of the Earth. We haven't explained where this value comes from, why the value is 9.8 meters per second square, and this equation explains why. So you get a value of 9.8 meters per second square for the acceleration of free fall because of the value of the mass of the Earth and the radius of the Earth you plug in. Okay, so these are the values that you plug in here: mass of the Earth, radius of the Earth, and g listed in this corner. And when you do the calculation, you end up with 9.8 meters per second square. Okay, so that's the story behind the acceleration of free fall. We get 9.8 meters per second square because the mass of the Earth is this and the radius of the Earth is this. If you have a different mass of the Earth, like for example, you go to a different planet with a different mass and different radius, you'll get a different value of the acceleration of free fall. Okay, or if you measure the acceleration of free fall above the surface of the Earth, like significantly above the surface of the Earth, then you'd have to plug in a different value of the r in the denominator, and you'd get a different value of g. You'd get a smaller value of g. Okay, so the value of g, the acceleration of free fall, is 9.8 meters per second square near the surface of the Earth, but as you go higher and higher, it deviates. It gets smaller and smaller. Okay, some questions to check your understanding. So question 1, is it possible for an object moving with a constant speed to accelerate? And the answer is yes, because the speed is constant, but the direction of velocity can be changing, like in circular motion. And if the direction changes, that counts as velocity changing, which counts as object accelerating. Question 2, an object moves in a circular path at constant speed. So compare the direction of the object's velocity and the acceleration vectors. Okay, so we know the velocity vector in circular path makes a tangent to the circle, and the acceleration vector points along the radius to the center. And if the velocity makes a tangent and the acceleration makes a radius, from geometry you know that the tangent and the radius of a circle always make a 90-degree between them, so they must be perpendicular. So that means that the velocity and acceleration for circular motion must be perpendicular as well. Question 3, what type of acceleration does an object moving with constant speed in a circular path experience? And the answer is centripetal acceleration, because the acceleration has to be pointed to the center, as we have seen already. Question 4, when an object experiences uniform circular motion, and uniform circular motions means circular motion at constant speed. So when an object experiences uniform circular motion, what is the direction of the net force? And the answer follows from what we had for question 3, that the direction of the net force must point in the same direction as the acceleration. So if the acceleration is centripetal, point to the center, then the net force must also point to the center. So the net force must be centripetal force. Okay, so let's continue with circular motion. So this object here is moving in a circle of radius r. Okay, and suppose we measure the angle from the x-axis to the line connecting the dot to the center. So this angle is theta. Okay, so this is known as the angular position of the particle. Okay, so as the object moves in a counterclockwise direction, the theta gets more and more positive, and then when the object completes half a circle, theta becomes 180 degrees, or that's equal to pi radians. When the object completes the full circle, theta becomes 360 degrees, and in radians it becomes 2 pi radians. Okay, so if the object is moving in a counterclockwise direction, we say that theta is positive, and if the object rotates in a clockwise direction, we say that theta is negative. Okay, so clockwise angle is positive, clockwise angle's negative, counterclockwise angle's positive, and the angles measured from the positive x-axis. Then we have the period. So as we defined earlier, period is the time to complete one orbit, one full cycle. And then we also discussed frequency. Frequency is the inverse of the period. So frequency tells you how many cycles the object completes in 1 second. Now let's compare the quantities in this table. On the left, we have the quantities for linear motion that we have seen already. We have position, velocity, and acceleration. So symbols are x, v, and a. And to find v, you just do delta x over delta t. Okay? And there are other equations of motion that we have seen already, but this is the basic equation. And to find the acceleration, you do delta v over delta t. Then on the right column, we have the corresponding quantities for circular motion, also called angular motion. So in place of position x, we have angular position, that's theta. In place of velocity, we have angular velocity with the symbol omega. And omega is calculated as delta theta over delta t. So you can see the similarity here for the velocity and angular velocity. You're considering the change in position for the linear velocity and the change in angular position for the angular velocity. And then for angular acceleration, you have the symbol alpha, and it gives you the rate of change of the angular velocity. Okay, so three corresponding quantities: angular position, angular velocity, and angular acceleration to correspond to the linear quantities. Okay, now how do we convert from linear to angular quantities? Okay, and here are some simple rules. So let's think of an arc length. So what's an arc length? So this is an example of an arc length. So we have this object, a pendulum, that's swinging. The radius of the string is r, and the angle the pendulum travels is theta. Okay, so this red line S is called the arc length. Okay, so that's the length that the pendulum travels along the curved path. So that's S, that's the arc length. And you can relate theta, r, and s using this equation. Theta equals s over r. And you got to be careful that the theta that you calculate from this equation is going to be in radians, not in degrees. Okay? All right, so this tells you how to find theta. And then the next equation relates the velocities. To find the angular velocity omega, you do the linear velocity over r. So omega equals v over r. And then to find the angular acceleration alpha, you do a over r. So alpha equals a over r. So basically, to convert from linear to angular, you have to divide by the radius, and you get the corresponding quantity in circular motion. And a quick note for converting from radians to degrees. So you can remember that pi radians always equals 180 degrees. So using this conversion, you can go from radians to degrees. So by dividing by pi, or you can go from degrees to radians by dividing by 180. So useful to remember, pi radian equals 180 degrees. All right, so this is the table that we discussed. Now, we have the four equations of motion for linear kinematics using x, v, and a, and t. And similarly, we have four equations for circular kinematics, where we replace the x, v, and a with theta, omega, and alpha, and the time remains the same. So you can compare the four equations there, and all we did was replace the linear quantities with the corresponding angular quantities. So the linear equations only apply when the acceleration is constant, and the circular equations only apply when the angular acceleration is constant, when the alpha is constant. So if the alpha is not constant, you can't use these equations. Okay, so this is something that we have seen already. We have uniform circular motion where the speed is constant as the object moves in a circle. So we have the velocity vectors that are tangents and acceleration vectors that point to the center. And then we have non-uniform circular motion where the speed is not constant. The object is speeding up while moving on the same circular path. So here you can see we have a small arrow for the velocity, but the arrow gets longer and longer at the other locations because the velocity is increasing. Okay, so in this case, look at the acceleration. So this dark orange line is the acceleration, and you can see in all 3 points the acceleration doesn't point to the center. Okay, that's because the object is speeding up, so the speed is changing, so the acceleration can be pointing the center. Okay, if the speed were constant, the acceleration would point to the center. However, let's take any of this acceleration, like this one over here. You can find the components of the acceleration that point to the center and then that point tangentially. Okay, so here we have this dark orange arrow, and you can find these components. Okay, and what are the components you want to find? The one that points to the center and one that points tangentially. And you can look at the 2 arrows here, the AC and the AT for this dot, the acceleration of this dot. And when you connect the AT and the AC, you will see that they start from the dot and end up where the original acceleration vector ends. So AT and AC are components of the acceleration A. So we can see that the AC component, the component that points to the center, is the same. I'm sorry, not the same. It's pointing the center no matter where the object is. And the AT component points along the direction of the velocity no matter where the object is. So we say that the AC, the acceleration that points to the center, is responsible for making the object move in a circular path, and the other component, the AT, which is the tangential acceleration, is responsible for changing the speed of the object. Okay, and to find the tangential acceleration, we can use the same conversion that we did a couple of slides ago. That tangential acceleration is the linear acceleration equals r times angular acceleration alpha. And here's an example of a pendulum that performs non-uniform circular motion. So you take a pendulum, pull it to some angle theta, then release it. Okay, so the pendulum starts from rest from the initial location, then it speeds up as it approaches the bottom, and then as it goes up on the other side, it slows down. So while it's swinging, the pendulum has non-uniform speed. Okay, it's speeding up and slowing down as it moves up and down the swing. So this is an example of non-uniform circular motion. And let's look at the forces acting on the pendulum. So we have the force from the string, and then we have the weight of the pendulum. Okay, so the forces, the weight isn't shown here, and the tension isn't shown here either. However, you can combine the tension and the weight, then break them up into components, and you can find 2 components that look like this. You will have a component that points in the direction of the string, which is the direction of the tension really. Let's call it FC. And also you will have another component that points the direction of the tangent. Okay, so that's something you get from finding the components of the weight. So this Ft, the tangential force, is responsible for changing the speed of the pendulum, and the Fc, the centripetal force, is responsible for keeping the pendulum moving in a circle. Okay. All right, and remember, these are the quantities that conversions you can use to go from angular to linear, and then a couple of bullet points. If the pendulum speed is constant, it would count as circular motion, uniform circular motion, where the tangential force is 0 and the tangential acceleration 0, and the omega, the angular velocity, will be constant. And if the speed is not constant, then the tangential force is not 0 and the tangential acceleration is not 0. So basically there's a force pulling the pendulum this way, and the speed and the angular speed will not be constant. They will be changing, increasing or decreasing. Next we move on to the study of rigid bodies. So we have earlier looked at particle model. So we assume that a particle represents an object. And that's reasonable for many purposes, but sometimes representing a particle, sometimes representing an object with a particle isn't sufficient. You have to represent it as an extended rigid body to show the different forces. So this brings us to the study of rigid bodies. We'll study the motion of rigid bodies. So to study the motion of rigid bodies, we introduce different quantities. So here's one of them, the torque, the quantity torque, with a symbol of tau. So what is torque? torque is the tendency of a force to cause or change rotational motion. All right, so in brief, torque is a turning effect generated by a force. So when you apply a force on a rigid body, it can create a turning effect. So we say that the force creates a torque on the rigid body. So here's an example. We have this door. We are looking at the door from above, the top view. So we are treating this door as a rigid body. So we have drawn this beam to show the door. So we haven't used the particle model. And we apply all these forces on the door, and it's hinged on the left. So which force out of these four will be the most effective in opening the door? So in other words, the question is asking which force will create the maximum turning effect and make the door turn. Okay. So the answer is F1. Okay, so why is F1 more effective than the others? Okay, so for one thing, F1 is acting far from the hinge. Okay, so compared to F4, F1 is further than F4. And then the direction of F1 is acting straight up. So F1 makes a 90-degree angle with the door. So F1 is perpendicular to the door. Okay, so F3 also acts at the same location, but F3 is not perpendicular, so it won't generate as much torque. And then F2 acts further from F1, so it's acting at the end of the door. However, the direction is pointing in the same direction as the beam. It's pointing towards the hinge, so it produces no turning effect. So we can see there are the number of components that are important here. First is the strength of the force. So bigger force creates bigger torque. That's one thing. And then also location of the force. Further from the hinge produces a bigger torque. And then the direction of the force. If the force is perpendicular to the line joining the hinge to the force, then the torque is also a maximum. Okay, so this also implies that this hinge is an important point. Okay, so this is the same as the pivot. So what's a pivot? Pivot is just a reference point, and when you're calculating torque, you have to calculate the torque with reference to the pivot, or we say you calculate torque around the pivot. Okay, and when the door is turning, you can see that the door can turn two ways, clockwise or counterclockwise. So the torque that we generate on the door, it can be clockwise or counterclockwise around the pivot once again. All right, so important to know that a force creates a torque, and the amount of torque created depends on the pivot that you choose. So in this example, it makes sense to choose the pivot at the hinge because the door is turning around the hinge. However, you can choose the pivot anywhere. If you wanted, you could have chosen the pivot at the middle of the door. Although the door turns around the hinge, you could have chosen the pivot at the middle, or you could choose the pivot at the right end, or you can even choose the pivot somewhere outside the door, like over here. So pivot is just a reference point. You can choose it anywhere. And later on, we'll see that there are clever ways of choosing the pivot, but technically you can choose the pivot anywhere, and you have to calculate the torques around the pivot that you choose. So whenever you mention torque, you have to mention the reference point around which pivot, because without the pivot, the torque doesn't make sense. It's incomplete. Okay, so more on torque. So here we have a spanner. It's connected to this bolt over here. And you're applying a force close to the other end of the spanner in this direction shown by F. Okay. So let's assume the pivot is the center of the bolt. Okay, so we are trying to turn the bolt by applying a force on the spanner. So we are applying a force at this direction, and this angle phi is the angle between the force, the arrow for the force, and the R. The R is the distance of the pivot from the place where the force is applied. Okay, so if this is R and this is F and this is the angle phi, okay, so remember phi is the angle between the force and the radius vector that connects the pivot to the point where the force is applied. So then you can calculate the magnitude of the torque using this equation. Magnitude of the torque is R multiplied by F multiplied by sine of phi. Okay, and if you think about this, the F multiplied by sine phi, okay, it represents the perpendicular side of this triangle. Okay, so that's why another way of writing the torque is this, R multiplied by F perpendicular. Okay, but really it's the same as R times F times sine phi. Okay, because when you have the angle and you take the sine of phi, it automatically gives you the vertical component. Okay, all right, so another illustration of torque. Okay, so in the previous slide we calculate R as the distance from the pivot to the dot where the force is applied. Okay, and that's all right. And then we calculate the components of F. We found the Y component, and then multiplying that by R gave us the torque. However, you can do it a little bit differently. Instead of finding the components of F, you can find the components of R. So you can construct this triangle using the R as the hypotenuse, and then you have this a perpendicular component, let's call it R perpendicular, okay? And that's going to be the same as R multiplied by sine phi. And when you multiply that with the force, you get the torque, which eventually gives you the same equation. So this is just another way of interpreting torque, that torque depends on the force and the radius, but with the proper components. But either way, when you account for the proper components, you end up with the same equation. The magnitude of torque is R times F times sine of phi. Okay, we'll come back to torque later. So now let's look at the next concept, the concept of center of gravity. And for most purposes is the same as center of mass. So let's look at this gymnast in the picture. So for this gymnast, the weight of the gymnast isn't concentrated at a single point. So the weight of every point on the gymnast is shown by an arrow. So we have multiple arrows here showing the weight at different points of the gymnast. So basically the weight is not concentrated at one point, it's distributed all throughout. However, we can represent all these little weights with one big weight, one complete weight of the gymnast. Now, where do you draw this arrow from? Okay, because remember, location is important when you have a rigid body. So you draw an arrow from what we call the center of gravity, or also called the center of mass. Okay, so this single arrow effectively represents the the weight of all these points on the gymnast. Okay, so we'll see that the center of gravity depends on the shape of the object you're dealing with, and if you know the center of gravity and you put a support under the center of gravity, for example, like for this gymnast, if the gymnast was supported by a maybe let's say a stool maybe under the center of gravity, then this gymnast would be able to balance herself without any other support. Okay, so if you place a support under the center of gravity, it provides a normal force, and the normal force exactly cancels out the weight because the weight is acting from the center of gravity. So sure, technically every point on the gymnast has a weight, but the center of gravity is like the average of all these points. So if you place a support at the center of gravity, it can effectively provide a normal force to cancel out the weights of all the points on the gymnast. So that's the center of gravity. It's described up here in the text. It is the average location of the weight of the object. So that's the same as the location where the entire mass appears to be concentrated. Okay, keyword appears. It's not really concentrated at a single point. It's distributed all throughout, but it appears to be concentrated at the center of gravity. So let's look at some common shapes and look at the center of mass of these shapes. So let's start with a circle, and the center of mass is going to be right at the center. So pretty obvious. And then we have the rectangle, and the center of mass again is going to be a center. So you can draw two diagonals for this rectangle, and where the meet of the center is your center of mass. And if you have a rod, similar idea, the center of mass is going to be right in the middle. Okay, so in all these cases we're assuming that the objects are uniform. They're made of the same material all throughout. It's not like one side is denser than the other. Now the last example here, triangle. So now the center of mass is not going to be at the physical center of the triangle. It's going to be closer to the left side because there is more mass on the left side. So it's going to be somewhere over here. Okay. So if you do the correct calculation, you will see it's 1/3 of the way from one end to the other in both directions, left or right or up and down. It's 1/3 of the way. Okay, and center of mass can be used to determine stability. So let's look at some examples here. So here we have the same object, the black dot, and it's in 3 states. The first state, we call it stable equilibrium. So it's inside this half circle here, like it's inside this bowl, and it's at the bottom here, it's at stable equilibrium, which means if you push the object to the left or right a little bit, it will come back to this original stable position, to the bottom. So that's known as stable equilibrium. Even when you disturb the system a little bit, it still comes back to the stable position. Then, second picture, we have the bowl upside down and the object is at the top of the bowl. So, as long as the object remains exactly at the top, it's balanced, it's at equilibrium. However, if you displace the object a little bit to the left or right, it goes down, it slides down and doesn't come back up on its own. So that's known as unstable equilibrium, which means that if you disturb a little bit, the object goes away from equilibrium and doesn't come back to equilibrium automatically. And then the third picture shows us neutral equilibrium. So this object is now on the ground, and you can move the object left or right, it just stays there. Okay, so it's not going to come back, but it's not going to fly off either. Okay, so that's known as neutral equilibrium. Even by shifting the position, you haven't changed the equilibrium position. It's at the same height as before. Okay, now let's look at the other 2 pictures underneath. So we have this box here, and the center of mass is this cross, the mark with a cross, and you draw the weight from the center of mass pointing straight down. Okay, so we can see this arrow for the weight passes through the base of the box. So that's known as stable equilibrium. And so this object won't tip over, it will stay there. So now, suppose you move the object, you rotate the object until it looks like this. So the center of mass is located at the same point as before, but the box isn't vertical, it's slanted. So you draw an arrow from the center of mass pointing straight down. So this is the arrow for the weight. And you can see this arrow does not pass through the base. So the base is this slanted part now, and the arrow doesn't pass through it, which means that the box is not going to be stable, it's going to be tipping over. Okay. All right, so the center of mass helps us determine the stability of an object. And more on stability. So let's look at the 3 pictures here. The first picture, so this box, I guess it's an empty box here. This is the center of gravity, and you draw an arrow for the weight. And then you turn the turn the box until the arrow just passes through the corner. Okay, so this box is at the point of tipping over. It hasn't tipped over, so it's just at equilibrium. Okay, all right, now next picture, take the same box at the same angle, but this time fill up with some liquid, okay, or some heavy base at the bottom, like water or something. So now there is more mass closer to the bottom of the box, which means the center of gravity is not at the same place as before. It moves closer to the bottom. So center of gravity is over here. You draw an arrow like before, and you can see that this time, even with the same orientation as the first picture, the weight, the arrow passes through the base of the box. All right, so the box is not at the point of tipping over, it's at a stable equilibrium. So if you let the box go, it will come back to its stable orientation. So that's one way of increasing stability. And when we say increasing stability, we mean the angle at which the object remains stable. So we are increasing the stability by introducing a heavy box. Or another way is to do this, you increase the width of the base. Okay, so if you have a broader base, then even for the same center of gravity, you draw an arrow, the arrow passes through the base. So a broader base increases stability and makes it harder to tip over. You have to rotate the box to a bigger angle to make it tip over. So this question here asks for the center of gravity of this L-shaped piece. So this is an L-shaped piece made up of two rectangles, the upper rectangle and the lower rectangle. And we are given 4 points, A, B, C, and D. We are trying to figure out which point best represents the center of gravity. So let's look at the two rectangles separately. Let's start with the upper rectangle. So if you look at the upper rectangle by itself only and pretend that the lower rectangle doesn't exist, you will see the center of gravity of this upper rectangle is close to point D, maybe exactly point D, okay? And similarly, let's just look at the lower rectangle by itself. If we assume that the lower rectangle is isolated and there is no upper rectangle, then the center of mass of this lower rectangle is going to be close to point B, okay? So for the two rectangles individually, we have the centers at B and D. So when we combine the two rectangles, the center of mass is going to be somewhere between B and D, okay? So you draw a straight line from B and D, and the center of mass is going to be somewhere in between. So it's going to be at point A. That's the best choice we have. And here are equations for calculating the center of gravity from coordinates. So these are the steps. So if suppose you're given a number of masses, first you draw a coordinate system. Draw an x-axis and a y-axis, okay? And you can choose the origin anywhere you want. And then find the x and y coordinates of each particle. And then of course note down their masses as well. So once you have the data points, then you do this calculation. The center of gravity, the x coordinate is given by this. You multiply each mass with the x coordinate, then add them all up and divide by the total mass. What you get will be the x coordinate of the center of gravity of the whole system. And then repeat for the y coordinate. Multiply each mass with the corresponding y component, add them up and divide by total mass. That will give you the y coordinate of the center of gravity of the system. So let's apply the equations to this system here. So we have this object. It consists of 3 balls, 1, 2, and 3. And their masses are given 1 kilogram, 1 kilogram, and 2 kilograms. And they're connected by massless rods. So we can assume that these black lines don't have any mass. We are trying to find the x and y coordinates of the object's center of gravity. Okay. So let's start the usual way. Let's draw a set of coordinate axes. So we have to draw an x and a y axis, and we can choose the origin anywhere. So just for simplicity, let's choose the origin at point 2. It's just an arbitrary choice. I could choose point 1 or 3 or basically anywhere in the middle as well, but let's just do point 2. Okay. So draw it like this. So draw the x-axis, draw the y-axis, and make sure the origin is the same as point 2. And then we find the x and y of the masses. So for mass 1, so that's the 1 kilogram mass at the origin. Okay, so I'm sorry, that's mass 2. We have a coordinate of 0 and 0. Then for the other 1 kilogram mass up here, we have a coordinate of 0 and 1, and these are all in meters. And then the 2 kilogram mass has coordinates of 1, 0. Now we use the equations in the box. So let's start with the x. Okay, so let's find the coordinate in the x direction for the center of mass. So you multiply the x coordinate of each mass with the mass itself. Okay, so let's start with the 1 kilogram mass, multiply with the x coordinate, which is 0. So you do 1 times 0, which is 0. Then for the next 1 kilogram mass, you also have 1 times 0, and that gives another 0 in the equation. For the third mass, 2 kilograms, you do 2 times 1, right? So we write 2 times 1. So that's the only non-zero term. And then you divide by all the masses added together. So you divide by the total mass. That's going to be 4 kilograms altogether. So you calculate 2 divided by 4 gives you 0.5 meters. So we are done with the x coordinate of the center of mass. Then repeat for the y coordinate. So for the mass at the origin, you do 1 times the y coordinate, which is 0. So that's the first term here, 1 times 0. Then for the next mass, you do 1 times 1. Put it in the middle. For the third mass, you do 2 times 0. Okay, so that gives you another 0. And then you divide by total mass. So effectively, you're multiplying 1 with 1 and dividing 4, you get 0.25. So that's the y coordinate of your center of mass. So you mark the center of mass in the picture as 0.5 meters in the x-axis and 0.25 meters up. So somewhere over here. Okay, so that's the center of mass of this system. Now, the next concept we look at is the moment of inertia. The symbol that we use is I, and the unit we'll see is kilogram meter square. So what's the moment of inertia? It's the resistance to rotation. Okay, so suppose you're trying to turn an object, make it rotate. Okay, so depending on different factors, it might require a lot of effort to make the object rotate, or it might require less effort to make the object rotate. Okay, so this effort, it depends on something called the moment of inertia of the object around its axis of rotation. All right, so let's go over this in more detail. So this resistance to rotation, what does it depend on? So one thing, it can depend on the mass of the object that you're trying to turn, trying to rotate. And then it also depends on the mass distribution of the object around the axis of rotation. Okay, so what's the axis of rotation? So here are some examples. We have this object here like a dumbbell with two masses connected with a rod. And you can see that it's possible to turn the object around different axes. So you can hold one end of the object like this left end and then rotate it around it. So basically this left end will stay fixed and the right end will make a circle around the left end. Okay, so the direction of the rotation is shown by this arrow. So we say the axis of rotation is this yellow line passing through this left object, and the entire object is rotating around this axis. Or you can rotate the object like this here. So you can have the axis of rotation passing through the center, and the entire object is rotating around the center. Okay, so the axis of rotation is like a line around which the object rotates. Or the third picture here shows another way. You can have the axis of rotation passing through both the objects, this yellow line. So the object is returning kind of like in a path around this yellow line, so shown by this black directional arrow. Okay, so that's what the axis of rotation is. Gives you a line, an axis, and the object is rotating around that axis. Okay, so let's look at how moment of inertia depends on the axis of rotation. Okay, so let's look at this picture. So we have a triangle made up of three masses, M1, M2, and M3. Okay, and we are rotating the object this way. The triangle rotates around this axis, the black line, going around, shown by the arrow, going in the direction shown by the arrow. Okay, so let's try to calculate the moment of inertia. So how do you calculate the moment of inertia? Okay, so you need these quantities. You need the masses, M1, M2, and M3, and you need the R values. What's the R value? It's the distance of the mass from the axis. So for the three masses, you measure the shortest distance from the mass to the axis. That's going to be the R1, R2, and R3 for the three masses. Okay, so you measure the shortest distance, which is also the perpendicular distance from the mass to the line. And then you calculate moment of inertia with this equation. Moment of inertia is the summation of mass times r square. Okay, so this symbol is sigma, it means summation. So you take every mass and multiply with this r square, then add it up for all the masses. You'll get your moment of inertia. So here, let's start with m1. So you multiply m1 with r1 square, and then you multiply m2 with r2 square, and multiply m3 with r3 square. But of course, r3 is 0 because you can see the mass lies exactly on top of the axis. So r3 must be 0. So you add up all these terms, you get your moment of inertia. Okay, and the last term becomes 0 just because r is 0. So this is the moment of inertia of this triangle around this particular axis of rotation. So suppose we keep the same triangle but change the axis of rotation. That's the next picture, this one. So that's the same triangle, just drawn bigger. And this time the axis of rotation is not going to be this vertical line. So this time the axis of rotation looks like this. So this dot is the axis of rotation. So just pretend that you stick a pencil through this dot on the screen. Okay, so the triangle is rotating around that pencil. So it's like the pencil is like a fixed pole, and that's the axis of rotation, and the triangle, all the masses are rotating around this. So now you have the same masses m1, 2, and 3, but the r's are going to be different. You measured the r from each mass to the axis, so it's going to be like this. R1 is the distance of the center of m1 to the axis, and then m2, r2 is the distance of the m2 from the axis, and then r3 is similar. Okay, so you can see that the r values are not the same as the first picture. So just by changing the axis of rotation, you have changed the r values, which automatically means you change the moment of inertia. All right, so you can see that for the same triangle, you have the same masses, but you have different mass distributions. The mass is distributed differently depending on how you choose the axis of rotation, and that changes the moment of inertia of the object. So whenever you describe moment of inertia, you describe the moment of inertia around an axis of rotation. So the axis of rotation gives you a reference point for the rotation, so you have to describe the axis of rotation first and then calculate the moment of inertia. Okay, so in the previous slide, we looked at the moment of inertia of point masses. So we had a collection of point masses and we found the moment of inertia around an axis. So what happens if you don't have a point mass? So what if we have the objects on this slide which are non-point masses? What if we have rods or rectangles or cylinders, hoops and spheres? So in such cases, you cannot use the equation from the previous slide. You have to use calculus techniques. And when you do use the calculus techniques, these are the results that we come up with. So it turns out that for a thin rod, the moment of inertia for an axis passing to the center is this: 1/12 times the mass of the rod times the length square. And if you shift the axis of rotation to the end of the rod, to left or right and either way, then the moment of inertia increases. It becomes 1/3 mass times length square. So this is telling you that it takes more effort to rotate the rod when you fix it at one end, okay, because it has a bigger moment of inertia. Okay, another way to think about this: the mass is distributed further from this axis, and when it's at the end of the rod, compared to the mass distribution in the first picture. Okay, so if the mass is distributed further, then you have a bigger moment of inertia. And it's the same principle for the rectangles. So if we have rectangular slabs and you have an axis passing to the center, the moment of inertia is 1/12 times mass times a square. And you can see there are two sides here, A and B. A is the side that's perpendicular to the axis. And then if we shift the axis to the left end, or whichever end, then the moment of inertia increases to 1/3 mass times a square. All right, then moving on, let's move on to the cylinder. So we have a solid cylinder here, or a solid disk, either way. The moment of inertia is half times mass times radius square. Okay, and the axis of rotation is passing to the center. Okay. And if you have a hollow cylinder, a hoop, then the moment of inertia doubles. It becomes mass times r square. And the reason is that the mass is concentrated further from the axis. The mass is concentrated all at the edge instead of the mass being distributed throughout the cylinder here. So that means the distribution, the distance of the mass from the axis is bigger on average, and the moment of inertia increases. Okay. In both these cases, let's assume that the cylinder has the same mass m. Then let's look at a solid sphere and a hollow sphere, so a spherical shell. And it's the same trend. For a solid sphere, you have a moment of inertia of 2/5 mr square for an axis passing to the center. And for a shell, you have a moment of inertia of 2/3 mr square for an axis passing to the center. So we have a moment of inertia for different shapes. So as we discussed earlier, the moment of inertia depends on the choice of your axis, whether it passes to the center or somewhere else. And it also depends on the mass distribution. So a hollow cylinder versus a solid cylinder makes a difference.